Hey everybody, welcome back. Here we got chapter 8 this week. We're going to talk about um, other variable control charts. So when we're talking about all the control charts that we've been talking about, we talk mostly about X bar and R and X bar and S. Those are the type of charts that we want to use um, when we have a lot of data, a lot of like recorded, measured data type of stuff. So those are the things that we want to use, and that's normally when you're going to see something in the real world. That's what you're going to see is it's more the X bar and R or X bar and S type of stuff. So these are going to be more of the more obscure charts, but still very useful in a lot of regards, depending on what kind of process that you have and what kind of data that you're using here. Um, so generally, it's always, like I said, depending on the situation, you might have a lot of situations where you have a limited amount of data samples available, right? So you are, you're producing ships, you know what I mean? Like something that's not done very often, right? So you have something that's a very small amount of data in there. The process is going to change very slowly. So you can record all you want to, but you don't see any changes happening. So that's another reason why you would use some of these. You want to have the understanding of the trends in the process. Again, but from the standpoint of you're not having a lot of samples in there, so you still want to understand what the trends in the process are. So you want to study the variability due to several factors. So different things, just other than just maybe one measurement that you're looking at, things that are, maybe dependent on each other, or the correlation of a couple of different factors. You want to understand that. The monitoring the process changes associated with a particular characteristic over time, and I'm going to show you how that works as well. But it's a nice way to be able to do this easily without a whole lot of math and all this other stuff. But we'll look at that as well. In situations where you have a variable subgroup size, so the subgroup that you have changes, again, you're going to have not a lot of data, so your subgroup of that stuff is going to change. So that's going to change how you measure it and how your chart looks on that. And then comparing a product produced with just the tolerance limits alone. We'll see that later on as well. And then short runs and product changes. So stuff that, again, is not, you might be run like once a year, and maybe a product change, just trying to get ahead of what you might see on there, and then seeing if you're getting out of there what you are expecting or not. So this is a similar chart, but in the back of your book, in the back cover actually of your book, you'll see this kind of stuff here, right? So you've got variables data on here, and this is just, I just took a little snippet of something. And from that side, when you go to the top, it goes subgroup size equals 1, all right? So in this case, you're looking at central tendency. So you're going to look at an eye chart or an individual's observation chart. In the other side of it, the lower leg of that is variation. So you're going to have, again, a subgroup of size of 1 with the variables data. You want to understand just the variation, and so then you're going to use a moving range chart. So and so again, you're going to see this in the back of your book. It's a little bit different than exactly what you got, but again, it shows you in there, okay, here's what you have, the type of data that you have, here's what you're trying to look for, here's the sample size that you have, and then what kind of chart would you actually use. So just so you know, that's in the back of your book. Very, very useful in a lot of regards if you're trying to figure out, okay, what do I use for this instance type of thing. So speaking of individual and moving range charts, that's what we use for when we have the data collection in a very infrequent amount, right? So it's either once a day or on a week to week or a month to month basis. So very, very small amount of data is being able to be produced to be able to measure. And so the measurements are going to be like single values, or the number of products produced is too small for the traditional X bar and R charts, right? So if we can do anything, we'd rather have X bar and R because it's a very easy thing to do, and it's the norm of everything we have. And there's a lot of upsides too of like X bar and R and all that kind of stuff because it can show capability and all that kind of stuff. So so calculating here, so you have your XI, which is your each individual reading on there, and then your M is the number of readings. So you would have the summation of XI divided by M, which is the total number of the readings. And so that's how you would get your the average of your individuals for that. And then you want to try to calculate R bar, which is again your summation of the range individuals, and that's divided by M minus 1 on that one. And so the R individual I, the RI, is called the moving range, and it's calculated by taking the 2 consecutive data points. And so it has to come out as a positive, right? So if it comes out as a negative number, you're just taking that and making it a positive one. And then you place that first R value in the space for the second reading. And so then you would calculate this as follows here. So your upper control limit for your X is going to be your individual X bar plus it's that 2.66. And so if you see in your book, it is, I can't remember which one, I think it's, is it D2? But it's Z2, but again, it's from the table. So you would go to the table to understand what your estimated is going to be for your dispersion there, for your standard deviation, multiplied by your R bar. And then your lower control limit for your X is your XI bar minus 2.66 again, also multiplied by R bar. And that's because N equals 2, you're going to be able to look it up on the chart. I believe it's appendix 2, but you guys can find that if you want to. But this is all just kind of following the same kind of what's in the book there on page 261. And then your R is your upper control limit equals 3.27 multiplied by your R bar, and then your lower control limit R equals 0 in this case. And so that's again N equals 2 on that one. And your lower control limit, because your ranges can equal 0, you have that just becomes 0. So your R bar is going to be anywhere from 0 to 3.27, and so that's what it looks like there for individual moving range there. So moving on to moving average and moving range charts. So in here, we're going to combine a number of individual values to create an average. So when a reading is taken, we would discard the oldest value and combine the new value with the other values, right? So hence the term moving average. So if I got 5 pieces of data and I've got a new reading, I take the new reading and I lop off the oldest one that was there. So you're always going after a moving range from that perspective. The control limits are calculated using the formulas for X bar and R charts, like we talked about before. And then the moving averages smooth out the short-term variation and allow it to be useful for studying for the underlying trends in the data. And so you think about seasonal products for this kind of thing, right? So it's trying to smooth it out so that we try to understand, okay, what are we trying to, what can we predict out of this using the averages over that? So seasonal products are like, Christmas trees or, farm goods, that kind of stuff. So seasonal type of stuff. But The weakness on this one is that the moving average will always lag, and so when you're doing it, you're still using the average from a couple months ago, and so it just the changes very, very slowly when you're adding the new one in, because you're using a lot of lag data to produce the numbers off of that one. So a good example on that one is in the book there, 8.2 on page 266. So check through that, but it's a nice way to do stuff for, like, especially seasonal type of stuff. Here's an all individuals chart. So in here you would plot each individual in a subgroup on the chart, and then you would chart the average with a circle. And then you can also include the range of the subgroup on its own chart below that. It's used to gain a clear understanding of how the data are spreading with respect to the average itself. A lot of times people say that it's kind of reserved for the training people on interpreting the values of R or S charts. And then again, you can look at page 8.5. Figure 8.5 on page 268, for example. This is not something, I'm going to be honest, this is not something I've seen used a lot. But again, it's just good to know the background of some of this stuff for this. But yeah, this one is not super important to me. I just want you guys to understand why you might use this and what it's used for. So multivariate analysis. Now, this is going to be used to help you clarify, study the spread of the individual measurements themselves. And that'll be in a sample and variability due to 3 or more factors, okay? So there is, it's very nice for the relationship between measured values. The book example, if you look at the chart that they give there, monthly sales data measured at the beginning, middle, and the end of the month, and it kind of gives you that understanding of how those things work together and how each of those measurements kind of line up with each other. So it's also nice for smaller point in time studies of variation. And but the weakness is you cannot judge if the process is under control. So you can't use for process capability calculations in that one. So this is one of the, like I said, some of the weaknesses of some of these charts are process capabilities are very hard or impossible to use for some of these. And then so using them doesn't always give you that capability understanding. So in this one though, again, you would plot the greatest and the least value in each subgroup on the chart and connect with a vertical line. And then include the specification limits on the chart themselves. You can see the 3 types of variation: piece to piece, between subgroups, and time to time. So again, that one is on 269. It is figure 8.7 on page 269 there. So the next one we're going to talk about is the median and range charts. So the median is a better measure of central tendency, right? So we want to understand what that central tendency, and then what then the mean itself. And so the example, the small sample size, where one measurement may be much larger or smaller than the others. So so that's a case that you would use it. So there's a lot of variation in the measurement of that larger, smaller sizes within the measurements you're taking. It's an easier calculation, but again, the trade-off, loss of sensitivity. So it's going to be really hard to see if the changes that you make are really affecting the process overall. Run charts is something. This is something that I use quite a bit, actually. Used to monitor the process changes associated with a particular characteristic over time. Where I work, we use run charts quite a bit, where we use them for kata. So kata, Toyota kata, another great thing to look up how to use all that stuff. But we use it to show the goal that we're trying to go for. We might be a performance goal. We have this many parts per hour that we want to put out. And so it's, hey, we're trying to shoot for 1,000 today. Oh, well, what did we hit today? We hit 700. Okay, well, great. We hit 700, but that's better than we have been doing, right? So in just a simple run chart, you can see as we're kind of going towards that goal of 1,000, how you're doing each day, just in an easy chart, so that we can see, okay, well, what things stood in our way of trying to get to 1,000 parts yet. So very, very useful. And it's easy to use right off the bat. Don't need any real math to go with it at all. It can be used with variables or attributes. And then the nice thing is there are no control limits. So you don't have to calculate all those, but it can't be used for process capability, obviously. Variable subgroup size. And so sometimes you're going to have, again, a process that's going to put out a ton in a day and then none at all, or very, very small amounts. So that subgroup size may change. And so you might make 100 one day and 5 the next. Or you have it where over time you just keep getting smaller. And so that subgroup size just keeps getting smaller. And then from that, you're going to see the control limits must be recalculated based on the new subgroup size. And so as you're changing your subgroups, that the control limits must change with it as well, so that you can see if the process is working or not. So each time that you change that subgroup size, it will have its own control limits. So and what you'll see is on that chart, it'll just have that, it just kind of keeps shortening and lengthening the control, what it looks like the control limits every time you change that subgroup size. So again, a good example of that one is on 8.13 on page 276. So you can check that out as well. Pre-control charts. So this is something that people call stoplight gauging charts. And these charts are used to compare the product produced with tolerance limits. So the assumption that you go into, you have to have a process that's already capable of meeting specifications. Don't use control limits on this one. So you're using specs and not control limits. And it can be, again, used with either variables or attributes on that one. It's very useful. Again, this is where I've seen it be used the most, is when you're doing like a setup operation changeover. You change a mold over, and you have to measure 5 parts or whatever to understand, are we capable right off the start, right? So we know it's a capable process. We know that we're able to meet the specifications, but with the changeover being such a big area of concern, when there's so many variation and so much change happening all at once, you just want to make sure that we're on pace to do it. And so you have the process setup, producing product centered within the tolerances themselves. It can also be used to monitor short production runs. But again, most of it's just trying to figure out how are we sitting right now. But it cannot, again, like most of these, cannot calculate the process capability itself. So so setting up a pre-control chart, and this is all right from the book, right? So you would just take that, the portion of your tolerance or your spec limits, and make it about 80–90% of what it is, so that you know that you're going to be well within it, depending on the expected process capability. Again, how critical is it? And then place those on the pre-control chart, and then determine the center of the specs, which is going to be the center line for the chart. And then so taking half the difference between the upper spec limit and the control, the center line, and draw a second line on that chart. So halfway between there, between the upper spec limit and the center line, and then also between the lower spec limit and the control line, you're going to draw a line halfway between those as well. So now you have 3 zones, which you have created there. Your green, which is going to be either side of the center line, halfway through up to the spec limits is going to be yellow, and then red is on the other side of both of the spec limits. So if it's way too high, out of the spec limit, is going to be red, way too high or too. So this is what ultimately it looks like. Here's you have your center line, and that's right in the middle of the green. And then, like I said, you have from the center line to the upper spec limit, 50% of that is green, and 50% of that is yellow. Same for the lower. And what you have then is you have a nice little chart to say, hey, we're starting something up. Where are we at? Are we in the green right away? Yep, we're right on track. Everything should be normal. I'm not worried about it. Take a few measurements here and there, and it's good to go. And so, but anything that's out of the spec limits is obviously bad. What happens with the yellow? Well, let's talk about that. So when you're doing it, you have the rules for interpreting how the chart and when to continue running the process, or when to let it go or stop or whatever. So here's the rules normally used for this kind of stuff. So if a measured part is in the green zone, just keep running, right? Makes sense. If the next part is in the yellow zone, check the following part after that one. So I ran a yellow one, check one more yellow. If a second part is yellow, reset the process. Go back and say, okay, something's not right. I didn't hook up a water line, or something's off. Some setting is off. Double check all your settings and ensure that it's good. If a part is in the red zone, stop, make corrections, and reset the process as well there too. So kind of 2 yellows, and then red, stop right away, make corrections. Understand that you might escalate to somebody who needs to know about that, and record it on a graph or whatever, on a chart, a separate chart, just to ensure everybody knows what might have happened. Again, you want to use that to make sure that we get rid of all the variation that's in there. If I forgot to hook up a water line, how do I fix that, and how do I make that so it can't be done again that way? And then 2 consecutive parts are outside the green, but they're on opposite sides. Again, take the steps to reduce variation in the process. So that means, again, you have one in the yellow, say on the high side, so it's in the yellow towards the upper spec limit, and then you have the preceding part after that is in the yellow, but it's on the low side. So you have a lot of variation going from one to the next, right? So that's again, another one is just to go and stop and double check and make sure everything's cool. Because again, you want to make sure that you hit it right off the bat and not create a whole bunch of scrap. And then whenever the process is reset, you want to see 5 successive parts inside the green zone. And then you can go back to your normal sampling plan that you might do, which is maybe you check 3 per hour or whatever, to ensure that. So that's like I said, that's a useful one. You guys can use that a lot, especially when you're doing setups and that kind of stuff. So and then the last one we're going to talk about is short run charts. Just as production gets shorter, the life of the product might be getting old. You're going to use short run charts, hopefully you'll be able to use this to at that point you have enough data on a lot of these things that multiple part numbers then now can go on the same chart. So the multiple part numbers, they all should be from the same family. They should act the same, so that it's a very, very similar type of product that's maybe always been separate, but when they get to low enough so that they can have enough data on there to have it all on one chart with the same product, the same part numbers, all that kind of stuff. But it has to be within reason and make sense when you use that. But then they enable users to view the impact of variation on both the process and the part numbers, all the ones that are included on that short run chart. So the data, regardless of the part number, are scaled to a common denominator, so that there's common distribution and set of control limits for all of those. So, and then a nominal X bar and R chart is then created off of that. So the critical assumptions that you have to use for for some of these short run charts is process variation, as seen on the range chart, is similar for all part numbers. So samples should still be from the same machine, operator, material. So making sure that we have still some semblance of order on that, and it doesn't just become kind of a free-for-all with all different machines and materials and everything else. So we want to kind of keep it within the family there. So, and then for an example on that, you can see the example on 8.8, which is on page between two. Yeah, so it's the example 8.8 is the problem in there. It's pages 280 through 282. So. Yeah, and that's just that part should be similar in nature there. So anyway, that is that's really all I have for today. So I hope it's going well for you guys. And if you guys have any questions about that, please again feel free to contact me, and we'll talk more about it. Anyway, other than that, have a great week, guys, and we'll see you soon.